Chapter 13, number 53. A 0.505 kilogram block slides on a frictionless horizontal surface with speed of 1.18 meters per second. The block encounters an unstretched spring and compresses at 23.2 centimeters before coming to rest. A. What is the force constant of this spring? So we're going to do this as an energy balance where the energy at the start becomes the energy at the end, where at the start we have only kinetic energy, 1/2 mv squared, but no spring energy. And at the end we have no kinetic energy, but 1/2 ka squared, in this case I guess with my notation, s squared, as the final potential energy. And then we solve it over, so we want k. So we cross multiply by 2 and get rid of the 2's. And we have mv squared equals ks squared. So k is mv squared over s squared, which gives us 0.505 kilograms times 1.18 meters per second, all squared. And then a distance of 23.2 centimeters, but I certainly want to convert that to meters to be everybody in the same units. That way I'll get newtons per meter, which is what I want. And we get 13.06409 newtons per meter, but having at best 3 sig figs, so we get 13.1 newtons per meter. Part B says, for what length of time is the block in contact with the spring before it comes to rest? And there's a temptation to maybe use kinematic equations and do like, oh, v squared equals 2a delta x, or x equals 1/2 at squared, but the acceleration is not constant. The force keeps changing as the spring changes its length. So we're going to have to be a little cleverer. Instead, we're going to say, if we look at the motion of this thing, the block does something along the following. It hits it, it goes to some max compression, it comes back to its original place, it goes to some max extension, and then it comes back to the original height. So under the assumption that the box stuck on the spring, then we would say that all of this is one period, and therefore this part must be 1/4 period. And even if the spring and box aren't stuck, it won't know that until the spring gets back to being at its equilibrium length. So for the first quarter period of this motion, or what would be this motion, this is what goes on. So we need to figure out the period, and that's not too bad because we know that the period is 2 pi root m over k, and our time is 1/4 of that. So we get 1/4 of 2 pi times the square root of 0.505 kilograms over the 13.1 newtons per meter. And I have to remember that there's a square root there as well. And so numerically this comes out to be 0.308 seconds. And then part C, if the force constant is increased, does the time required to stop the block increase, decrease, or stay the same? The time depends only on the mass and the spring constant. We can see that it depends inversely on the spring constant, so if the spring constant gets larger in part C, the time would become smaller. K going up means T goes down, shorter time.